I am Varun Bhalerao from IIT Bombay. I am an astrophysicist. I work on instrument development and in high energy astrophysics. And today we are going to talk about time domain astrophysics at high energies. So, transient and variable phenomena that are visible in X-rays and in gamma rays. So, just as a quick revision, the electromagnetic spectrum stretches all the way from extremely high energies, which is our gamma rays on this side going through X-rays, UV visible all the way to radio. And what we are focusing on now is this X-ray and gamma ray regime. You could either think of it in terms of temperature or in energies or in wavelengths. So, usually when you are talking of optical, for example, you talk of wavelength of light, but in radio waves you talk about frequencies. In the same sense, in X-ray and gamma ray astronomy, we usually talk about energies of the photon. So, we are roughly speaking, the X-ray band is something from about photon energies of about 100 electron volts to few hundred kilo electron volts, and few hundred keV or maybe MeV and higher is the gamma ray band. And that if we are looking of it in terms of an equivalent temperature of objects which would emit primarily at that, then we are talking about millions to billions of Kelvin temperatures. And you can see that this is radiation which is actually corresponding to size scales of atomic nuclei or atoms. So, extremely small wavelengths, angstroms to much smaller than that. What kind of properties should we be thinking about when we are talking about photons? So, the basic properties of a photon are summed up by this list which I have here, which is that we have a position of a photon, which is where a photon is currently present, what direction it is moving in. Then we have the energy or the frequency of a photon, which are just related by E is equal to h nu. We also want to know when the photon was here, because photons are constantly moving at the speed of light in that medium. And finally, the last property of a photon is the polarization, which is although you think of it, it is easier to introduce as a classical concept, but is equally valid and important in the quantum description of light as well. So, any ideal detector, what we want to do really is measure all of these properties of photons. And the great thing is that X-ray and gamma ray detectors simultaneously measure more than one of these properties. So, a typical X-ray or gamma ray detector will tell you where a photon landed on that detector. It will tell you what energy the photon had and when it arrived. Some advanced detectors can actually also tell you the time of arrival of these photons to very high accuracy, or they can tell you the polarization of these photons to very high accuracy. Gamma ray detectors can tell you the position and direction together and so on. This is very different from the optical or radio regimes that you have usually been thinking about, in which case you need an optical element which is concentrating those photons, but you usually will not get much idea. Say if you use an optical camera, it will simply tell you how many photons were incident. It will not be telling you energies of individual photons, and within the exposure of your camera, it will not tell you what photon came first and what came later. So, these measurements of these properties, high quality measurements and high precision measurements of all of these properties simultaneously make a huge difference in what kind of science you can do with these X-ray and gamma ray detectors. So, what science can be enabled? First we have to go back, although you have learned this in other modules, what are, let us do a quick revision of what are the sources of producing X-rays and gamma rays. And the sources that we have, first is of course you could have thermal emission, which can work in X-ray regime. If you have temperatures which are millions of kelvins, you can emit what are called soft X-rays with energies up to few keV. Those could be generated thermally, but by far the most common way of generating X-rays or gamma rays is you have plasma which is interacting with a magnetic field. So, you can start having various emission forms there, and then to generate that plasma, of course, you could have either a hot body, or you could be taking matter from one object and dumping into another, which is called accretion. So, if you have say a binary star, or if you have a giant cloud of gas which is accreting onto a central black hole in a galaxy, all of those forms are called accretion. In addition to that, you have radioactive decay, which of course is the conventional definition of gamma rays. You have an atom which decays and gives you either alpha, beta or gamma radiation, or you could also have fluorescence. So, all of these various properties, and then of course, there are other detailed mechanisms which we have studied in more detail in other lectures. This is not the time to go into detail for all of those, but it is all of these sources that are producing this radiation. And what is important is that all these channels of production of these radiation are variable. So, if there is any variation in any of these parameters, if we have for example, accretion going on to a system, and if the amount of matter that is falling onto the surface of say a neutron star or onto the disk of a black hole changes, then the total amount of intensity, the total amount of light emitted from that is also going to change. Similarly, if you have say high temperatures, but the source is heating or cooling due to some properties, then the amount of radiation that you are going to get, the spectrum of radiation that you get is all going to change. In fact, a large fraction of sources in the X-ray and gamma ray sky are actually variable sources, to the extent that it is extremely hard for us to find a source which is constant enough that we can use as a reference source. So, some of you may know for instance that in optical astronomy for a long time this object called Vega was the standard star. So, the brightness of every star was expressed in comparison to the brightness of a star called Vega. In X-rays, people began with a similar thing, and we used the Crab pulsar and nebula as our standard source for a long time. But when instruments became precise enough, we have now discovered that the Crab itself is a variable source. So, it is all sources vary to such an extent that it is very difficult for us to find a source whose intensity is not varying with time. So, time domain astrophysics is intrinsically a very important aspect of in general high energy astrophysics. So, what kind of variable sources do we have? The easiest source to talk about in terms of variables would probably be an X-ray binary. So, what I am talking about here, X-ray binaries could be are usually a compact object and a normal star, a main sequence star often, which are orbiting around each other. The compact object can either be a neutron star or a black hole. So, let us look at this particular example where I have actually drawn here. This is a neutron star or my impression of a neutron star, and here we have a giant star. Now, what is drawn around both of these stars together, it is what is called the Roche lobe. Very loosely speaking, you could call this the sphere of influence of this particular star. So, the lobe which surrounds this giant blue star on this side, this lobe is where if I release a test particle here, it will fall onto the blue star, whereas on this side if I release anything, it will fall onto the neutron star. And the size of the Roche lobe depends on the masses of both of these objects. As this blue star evolves, it can actually slowly end up increasing in size, and at one point it might actually overflow its Roche lobe. So, what it means is that as this material over here actually crosses beyond this line, what is going to happen is that it is no longer gravitationally bound to this star, and it may end up flowing all the way through onto this neutron star over here. So, now I am dumping a huge amount of matter from the outer layers of this giant star onto this neutron star, and that matter, all of its kinetic energy is getting converted into heat when it hits the surface. So, there is a lot of ionization, we are generating plasma, it can get coupled with the magnetic fields of the neutron star that we see here. We can have accretion onto the pole, and in general it is an extreme environment, extremely high gravity is causing high acceleration of the matter as it falls in, and that gives us high energy radiation. So, we will get emission of X-rays, sometimes even gamma rays from these kind of processes. But the source of all of this is how much matter is actually flowing out beyond this boundary and then making its way onto the neutron star. So, you can imagine that if there is any turbulent process going on on the surface of the blue star, then that is going to cause a variation in the rate of accretion, and that means that these X-ray binaries are often very variable. Not only this, there are sometimes cases where variation is even more extreme. So, here is another type of system that we have. We have the star which is shown here is blue, but those stars actually do not look blue. This is a B type star, but it is called a B type star with E ahead of it. That does not mean beryllium. It is a B type star that shows emission lines in its spectrum. And what we understand these stars actually do is that they actually have a disk in their equatorial plane. So, the star is large, it is spinning fast, and the surface velocity at the equator is actually high enough that you can start losing matter from there, and this matter settles on to a disk. Now, suppose I have a neutron star over here which is in this high elliptical orbit around this B type star, and which is shown by the green line in this slide. What will happen is that as the star plunges through this equatorial disk, it is suddenly going to get a lot of material accreted onto it. So, we can actually try plotting this. So, what is plotted here on the y axis is the rate of accretion dm dt, how much matter is falling onto the neutron star as a function of time, and I am going to plot it as the neutron star actually goes around this orbit. So, if we look at this animation now, as the neutron star approaches and it plunges through the disk twice, once while coming close to the closest point which is periastron, and then again while going away, there are two episodes where the rate of accretion actually increases, and that is really when you see a large amount of X-ray emission from these systems. Pretty much that is the only time when several of these systems are visible. So, there can be very extreme episodes of accretion which can cause extreme variability in such sources. Speaking of neutron stars though, there is another type of variability that is intrinsic to a neutron star. So, imagine this scenario where we had again a neutron star which has a magnetic field, accretion is going on from a companion. Because this material is very likely to be ionized, it couples with the magnetic field lines of the neutron star, and the neutron star will then drive all of this material accretion onto the magnetic poles of the neutron star. But the neutron star itself is spinning. So, what happens as a result is that you are seeing different parts of the neutron star surface as a function of time. So, imagine if this were a neutron star and accretion is happening at these two ends of the neutron star. As it spins around, you are sometimes seeing a spot where matter is landing, and sometimes it is pointing away from you. Then you start seeing the other magnetic pole, you could call them the north and south poles, and then you are seeing nothing again. Of course, the field is not ideal dipole field, there are many complicated components to it. So, the net result of all of this is that you see intensity of X-ray emission which changes as a function of what angle you are viewing it at. So, these graphs which are plotted here are showing this intensity variation in different energy ranges. So, at the top I am plotting intensity from 3 to 6 keV, whereas and going on to higher and higher energies, whereas this bottom plot here which you can see is a lot more noisy, because the neutron star is actually emitting less radiation there, and that is at the highest energies of 4 to 80 keV. And on the axis at the bottom, what is plotted is a number that goes from 0 to 2, that is simply the phase of rotation. So, when the neutron star is at a certain orientation, I call this phase 0, when it completes half a turn it is phase 0.5, full turn is phase 1, and then I am plotting 2 turns. So, it goes to phase 1.5 and phase 2. And you can see that at different energies the pulse profile actually looks different. So, this plot is called the pulse profile. The neutron star, as you can see, there is a peak somewhere here, and then one cycle later at this point there is another peak. So, and then there are dips in between. So, you see this up and down variation of the intensity of this neutron star as a function of time, and it is different at different energies. And all of this is exactly what we look at, and this is exactly what we study to try and figure out what exactly is causing the emission. What component of this is coming from, say, thermal blackbody emission, what could be coming from Bremsstrahlung, is there any Compton scattering going on, inverse Compton scattering going on, are we seeing any magnetic field effects causing cyclotron radiation. So, all of this we can understand by studying these kind of pulse profiles for neutron stars. Giving another example of extremely variable accretion on neutron stars, there is a class of binaries called supergiant fast X-ray transients, or SFXTs for short. So, what is plotted here is a soft X-ray light curve of a SFXT called IGR 17544 minus 2619. So, this name which you see over here 17544 is simply the right ascension, 17 hours 54.4 minutes, and 2619 minus 2619 is the declination of this object, minus 26 degrees 19 minutes. And what you can see here is that the count rate or the intensity actually varies quite a bit. There are all these periods which are marked here by just downward pointing arrows. This means that the source was too faint to be seen by this particular telescope, and then there are spikes like this where the source became extremely bright, and on this plot itself you can see that it varies by more than 4 orders of magnitude. In fact, people have taken more sensitive telescopes and pointed to this chap when it was in a phase we call quiescence, where it is not being seen, which corresponds to these upper limit arrows over here, and Chandra measurements show that the source brightness is sitting somewhere here. Chandra is a more sensitive X-ray telescope. So, you can have these objects whose total brightness is varying by a factor of 1 lakh. In astronomy, we are used to seeing very large numbers, so it is easy to forget the implications of this. But remember that the brightness of the sun, even if it varied by as little as 10%, that would be catastrophic for our space weather and for our atmospheric phenomena and so on. This object is varying by a factor of 1 lakh. And this variability again has to do with accretion being non-homogeneous. There are various theories about this, we are still completely trying to understand the phenomena. But what is also interesting is that in these changes in brightness, you can have a factor of 10 change in brightness in a matter of something like few minutes, extremely rapid variability, and this would not be possible with a thermal kind of source. There are other types of X-ray binaries. Of course, we have been talking about compact objects, but so far I had limited myself to neutron stars mainly. But here is an artist's rendering of a black hole called Cygnus X1. Again, it is a binary star. You can see a blue component there, which is a large star from which matter is being drawn onto the black hole. But what you see is that there is an accretion disk around the black hole. So, this matter settles into a disk and slowly propagates through this disk onto the central black hole. The black hole itself, of course, is black, it does not emit any light, but you can see these two large jets that are being launched from the black hole, and that has to do with how the interaction of the magnetic field and the matter that is moving into the source at this point, it launches jets often. Okay. And when you say that we observed a black hole, what you are really talking about is emission coming from the surrounding regions of the black hole. So, this accretion disk here is what scientists are looking at when they say we are measuring properties of the black hole. So, the emission is really coming from the accretion disk, and the total properties of the emission are going to depend on what is the total accretion rate onto that black hole, how much matter is falling in. Of course, it will depend on the black hole mass, because the more the mass of the black hole, the more kinetic energy this matter is going to get as it is falling in, and then that is also going to be finally the total amount of energy that is radiated away. And it also depends on a property called the spin of the black hole, which changes the dynamics of space-time near to the black hole. Okay, so, by studying all of these sources, by measuring this light and its spectrum and its variability, we can actually start understanding properties of those central black holes. So, I will give you a few quick examples about what kind of properties we can measure. So, here is an observation actually taken by LAX PC, which is a detector on India's very own AstroSat. So, on the axis here at the bottom, you are seeing frequency in hertz. So, this here 0.1 hertz is where you would be seeing one oscillation per 10 seconds, and here is 1 hertz where you have one oscillation per second, and it goes to about 20 hertz or so. And you can see that there is this huge spike there in between, and then a second spike which is at 1.5 times higher frequency. This is something which is seen in a lot of black hole binaries, and these are something called quasi periodic oscillations, or QPOs for short. So, what is quasi periodic oscillation? Well, you see some periodicity, but it is not coherent. So, if you actually took this light curve and you looked at it, it would not nicely show the same consistent variation like a pulsar. But if you took something equivalent of a Fourier transform, or here what is plotted is a PDS or the power density spectrum, then you see these spikes. So, there is more power present. So, there is these two frequencies seem to be related to some fundamental frequency of that system. And what we relate this to is very likely the orbital period or the orbital frequency of particles at what is called the ISCO, or the innermost stable circular orbit. So, in a relativistic description of a black hole, you cannot have stable orbits that are very close to the surface of the black hole or to the event horizon of the black hole. And the last point at which you can have a stable circular orbit is called the innermost stable circular orbit. So, any accretion disk that has been found will naturally get truncated at that point, because beyond that matter should very likely just free fall into the black hole. So, you have all this stuff going around, and any disturbance that you get at that point is going to show you oscillations for a little bit until that blob of gas or whatever was causing that disturbance, was causing that oscillation, actually manages to fall into the black hole, and then that disturbance is lost. So, you see variability for maybe a few cycles, then the source of that variability disappears. but a new source pops up again on the ISCO at some other point of the ISCO. If the first one was here, the next one could be here. So, it appears to be at a different phase, but it still has the same period. So, again by just measuring the frequencies of these and how they change with time and so on, we can actually start measuring masses and spins of black holes. And black holes actually, if you look at it as an astrophysical system, it is an incredibly simple system. An astrophysical black hole is charge neutral typically. So, it is completely described by exactly two free parameters, the mass and the spin. So, you would expect, if you do a naive extrapolation of this, that the system should behave very well and very easily understood, simple to model, but that is not at all the case. So, here is a bunch of light curves or observed variabilities of a black hole. Okay. What is pointed, what is plotted on the x axis in each of these graphs is time in kiloseconds. So, this each of these extends for roughly 3600 seconds. So, just about an hour, and these are observations on different dates. Okay. So, the dates are actually written at the top of each graph, or you can, so any of the plots that you are seeing in my talk, I have put in the references for the papers at the bottom. So, you can go and look at this data in more detail if you want, but this is the same object observed on different days, and you can see that on every different day it can actually show you a very different face. And all of this has to do with these dynamics and feedback loops running in the accretion disk and so on. So, it is a very rich field to just study this and try to understand what exactly is responsible for these kind of variations. There is some progress about this, and in general we see that black holes actually follow this kind of path on something called the hardness intensity diagram. Okay. So, as I have said here, hardness is a proxy for spectral shape. So, I cannot always go and get a full detailed spectrum of a black hole, that requires me to have a lot of time on a large telescope, which may not be feasible. So, what I say is that, is the source relatively hard or relatively soft? There is a quantitative way of describing it, which is the flux in one band divided by the total flux you measure in another band. So, flux which you measure from say 20 to 40 keV divided by flux measured in 10 to 20 keV, it depends on what instrument you are using. Okay. So, a harder source is emitting more, relatively more photons at high energies for every photon it emits at low energy. And in case of black hole binaries, what we actually have observed is that they start in the corner marked A, and the source. So, on this axis at the bottom I have hardness, and the far right corner of the slide over there is a very hard source, closer to me here is a soft source, and upwards is a brighter source. So, the source starts in that corner, it slowly becomes brighter while remaining very hard. Then at the high intensity itself, it comes closer and it becomes soft, and only after becoming a soft source does the luminosity drop. It does not drop all the way to 0, it remains at this level here, and then it goes back into that side and then goes down into that corner back into the hard state. So, these kind of observations are what people begin with. As you see, the luminosity is changing quite a bit along this axis, and this variability continues, and we have seen this for dozens of black hole sources by now. And these kind of diagrams again allow people to compare different sources with each other, try to understand what properties, and we now have physical interpretations for what each of these transitions here mean. It has to do with how large the accretion disk is when a jet is being launched and so on. So, speaking of black holes, not all black holes are in binaries, there are much larger black holes that are present. So, what you see in these slides behind me now, the image that you see here is actually an infrared image of the center of our own galaxy, of the Milky Way galaxy, and the very central center of our galaxy is an object which we call SGR A star. It is a supermassive black hole which is about 4 million times the mass of the sun, and this large image that you see over here is an X-ray image, a hard X-ray image of the galactic center taken by a space telescope called NuSTAR. And what you see on the far right in those series of images over there is an image of the central black hole of our galaxy at 3 different times, and you can see that the source is significantly brighter in the middle image. So, this is what was called as a flare of the source, and what we think happened here is that this is what the source looks like normally, and at this point something must have fallen in and gotten disintegrated. One possibility is that the amount of mass needed to do this is roughly the size of an asteroid. So, if an asteroid fell in, you could think of it as our galaxy having snacking on asteroids essentially. So, if an asteroid fell in there, that extra energy was suddenly released, as a large burst of hard X-rays, and then at the bottom here you can see that the source went back to quiescence. Okay, so, these kind of variabilities are seen in neutron star sources, in black hole sources. It could be intrinsic variability, extrinsic variability, and this is being studied by high energy astronomers using a large set of telescopes around the world. Having talked about variables, now that brings us to transients. The difference between transients and variables is not very large. Basically, a transient is a source which you were not seeing until say today, and suddenly today morning it appeared, which means that if you are looking at say a variable object like the SFXT that we talked about, and your telescope is not sensitive enough to see it in its faint state, then you would call it a transient. So, we will not dwell too much on the difference between this, but now I am going to introduce you to a few classes of transients. Not all of these are unique to just high energy astrophysics. There are several of them which are studied, or almost all of them these days are studied in all wavelengths. So, if you are looking at the module components for optical time domain astronomy or radio time domain astronomy, you are going to have come across some of these as well. So, the first object that we will talk about is one whose name itself implies that it is a high energy source, and that is gamma ray bursts. So, there is an interesting history part of this. Gamma ray bursts were actually detected when Americans had launched satellites to monitor Soviet nuclear tests, and they had multiple satellites which were trying to triangulate where the test was happening, and when they tried to find a solution, they realized that the explosions were not actually happening on ground, but they were happening in space. So, what exactly are gamma ray bursts? Well, one type of gamma ray burst is actually a massive star which blows up, and again because of the way the supernova explosion is happening, you can actually end up launching these two massive jets from both the poles of the object, and for an observer who is along the direction of that jet, because of relativistic beaming, you can suddenly see this extremely bright source, and these are so bright that we have seen them practically across the universe. We have seen them at extremely high redshifts as well. For all other observers, this would look like a regular supernova, and which means that it would take, you would see it in optical wavelengths of course, and you would typically see it brighten after a few weeks after the explosion. But the gamma ray burst itself lasts for at most minutes, and that is it. So, these are, wherever these were nearby enough for us to study them in detail, we have always seen the supernova. So, we know that these so called long gamma ray bursts or long soft gamma ray bursts are coming from this. But these are just one type of gamma ray bursts. There are actually, what people did was that when a lot of gamma ray bursts were detected, they started again making a plot where on one axis you have the hardness, which is the vertical axis in this plot over here. So, essentially how many photons do I see in hard X-rays versus soft X-rays, and on the bottom axis over here is the duration for which you saw the gamma ray burst. And you can see that there is one clump over here, but there seems to be this other loose clump of bursts over here. So, you can actually separate them into possibly two categories, and these two categories then were called short hard bursts and long soft bursts. So, these ones over here, long soft bursts, we now know that they are coming from the explosive deaths of very massive stars, and if we happen to be along the axis, which is roughly 1% is the beaming angle. So, roughly 1% of observers in the universe would be able to see this as a gamma ray burst. The remaining observers would just see a supernova if they went and looked for it. But what about the second category of bursts over here? These we believe actually come from mergers of two neutron stars. So, what is shown here is snapshots from a simulation. So, this is a GR-MHD simulation, a numerical simulation that involves general relativity and magnetohydrodynamics. This is pretty much the most complex simulation that you can ever undertake, and the 6 panels here show a process in which two neutron stars actually merge with each other, and in the process of merger, the lines that go through all of these, for example, the lines that you see here, these are tracing the magnetic field of the neutron star, and then what you can see finally is that the magnetic field itself, the final configuration is such that you can end up creating two jets coming from that. These bursts last for less than about 2 seconds. That is the rough split that is used in differentiating between long and soft GRBs, but remember that that is just an observational consistency, observational condition. You can see that in this diagram there are bursts here which are quite long in duration. This one for example would be about 10 seconds in duration, but is a short burst. So, it very likely arose from the merger of two neutron stars, whereas this burst here which lasted for just about a second very likely came from a supernova explosion. So, you have to keep in mind that some of these differences are phenomenological, they are observational, they are for convenience, but they are only an indicator of the underlying physics. That is not necessarily a final verdict. The final verdict always should deal with the physics of the source, what exactly happened at the source. So, what does a GRB look like? How do you actually detect one? So, I will show you an example here. This what I am going to show you over here now is what data from one of the instruments on AstroSat looks like. This is an instrument called CZTI, the cadmium zinc telluride imager on AstroSat, and it has detected close to 200 GRBs in 3 years of operation. Okay, so, what is plotted here right now at the bottom is the usual count rate. So, how many photons does CZTI receive per second? And what I am going to do now is I am going to advance time, okay, and we will see what kind of a burst would be seen by CZTI. So, as time goes on, suddenly the count rate which was usually hanging around 100 counts per second shot up all the way to close to 2500 counts per second. You can see that there are multiple colors used in this graph and they are labeled as A, B, C, D. Those are the 4 identical quadrants of CZTI. So, these are 4 identical, you can think of it as an instrument made up of 4 sub instruments, and these are the 4 identical sub instruments, and the burst was seen clearly in all 4 of them. This particular one was a short GRB, that is why you can see that the peak over here is extremely narrow. The width of this peak is actually for this particular one is close to just about 1 second. Another important fact that I have written out here is that these detectors have to be space based. Fortunately for us as human beings living on earth, the atmosphere is opaque to X-rays and gamma rays. That means every time the sun has a solar flare which emits a lot of X-rays, it does not actually affect life on earth. It does not end up completely cooking everything on earth because the atmosphere completely blocks it. But as high energy astronomers, that is an unfortunate thing for us because it means that we cannot do any of these studies from the ground. We necessarily have to be either on rockets or in satellites, which is the most common thing now, because it gives you a stable long term platform, or if you are actually developing an instrument and if you want to test it, you can put it on a hot air balloon so that it goes to a very high altitude. Depending on where you have launched from, your flights could last for few hours to few days, or sometimes if you are lucky a bit longer. You do your experiment on that because you are above most of the atmosphere and then you process your data after that. Okay. So, the next class of transient is something called tidal disruption events. So, what exactly is tidal disruption? We have all heard about tides, of course. On earth we know what tides are. The gravitational force of the moon actually enforces, it causes motion of water on earth and it causes the oceans to bulge out a bit, which gives us high tide and low tide. Now, imagine if you are a star that is sitting close to a supermassive black hole. So, this is a diagram drawn roughly to scale. This is what the size of the sun would be as compared to that big black circle over there, which would be the event horizon of a non-spinning black hole, which is a million times heavier than the sun. Now, these two are separated by some distance d, but the star itself, the radius of the star is not very small as compared to this d, which means that on this side of the star versus this side of the star, the gravitational force exerted by the black hole is different, and if you come close enough to the black hole, then this difference in the two gravitational forces can actually end up being larger than the gravity of the sun like star itself. So, you can actually end up completely ripping apart the star, and this is called a tidal disruption. So, what happens is that not all stars in galaxies are in standard circular orbits. In fact, probably most of them are not in closed orbits because the system is highly chaotic. So, if a star somehow ends up getting thrown inwards in a galaxy and passes very close to the galaxy center, to the black hole, it might actually get completely torn apart, and all of that material then can form an accretion disk. It can again launch jets, and if those jets are pointed towards you, then you will see it as a high energy transient, and of course, you can then go on and study it in other wavelengths as well. So, these events often discovered in X-rays and gamma rays, but they are now studied in optical, infrared, radio waves as well. So, what I am going to show you next is a simulation of such a tidal disruption event done by a group. So, follow that arrow, and where the arrow stops around now, keep your eye at that place. Okay. There is a star that will begin there as the animation begins round about now, and there it is. So, the star went too close to the black hole. You can figure out where the black hole is, which is somewhere around here, and you can see that the star, which used to be one nice solid body, has completely become disrupted. This huge plume of gas is now being stretched out completely, and whereas here you can see a lot of activity happening. There is a lot of accretion going on to the black hole. You can see there are a lot of instabilities and so on, and that is what is causing the full tidal disruption event. And here is a mystery source that we studied in 2018, quite an interesting source. The name of this source, which you can read here, is AT 2018 COW. It is not because we actually found a cow in space. What we do is AT simply stands for astronomical transient. So, this was an astronomical transient discovered in the year 2018. The first source discovered in this year was called 2018 A, then the next one was 2018 B, until we went to Z. The next source was AA, AB, and so on. And by the time this particular source was discovered, the name actually was COW. So, it is a mere coincidence. This was a transient in a nearby galaxy. So, not in a galaxy long time ago, far away, but I have put nearby in quotes, and that is because you have to realize that this is in astrophysical context. So, by nearby, this was about 60 megaparsecs away, which is about 200 million light years, give or take. Okay, so, quite far away. This source has been studied quite extensively in a lot of wavelengths, but we still have no idea what it really does. Okay, so, what you see here, all of these black dots, you can ignore the red markings over here, but all of these black dots which are plotted with error bars are measurements of the X-ray intensity of this source, and time at the bottom is plotted as time in days. So, these are observations spread over roughly 1 month. Now, you can see there are two dashed lines that are plotted there. There is a yellow orange line which has a, this is a log linear plot. So, it is a, this is a power law, but it does not look like a straight line here. The yellow line is broadly speaking the kind of time evolution you would expect from a regular gamma ray burst. The blue line is the best fit that was observed for this source, and if you had so it has a slope of minus 0.5. If you had a tidal disruption event, you expect a slope of minus 0.6. So, this source kind of shows some properties that are like supernovae, it seems to show some properties that are like tidal disruption events, and despite multiple teams around the world working on this, and there are within about 3 months or so, there were 3 or 4 different papers published on this, but unfortunately we still do not know what exactly this source was. And that is the very reason I am putting this here in this talk, because astronomy is in that sense a physical science which is different from the rest of our physical sciences, where we are doing experiments, but we have no control over the experiment, and that is a very important point. Okay, I cannot go to a lab and say, okay, let me take a star and put it into a black hole. I cannot go and light the fuse on a star and tell it to explode as a supernova. I have to wait for the universe to do these things for me, and I have to be alert, and I have to catch these things in the act, and then I get to study them from only one angle. I cannot say, let me go around and look at this star from the other side to figure out what it is doing. Okay, and that puts very severe restrictions. So, everything that we know about the universe is from studies like this despite these limitations, and that is quite an achievement for all of humanity. So, let us talk about one more kind of transient, which is something which I am sure everyone has heard of, which is gravitational wave sources. But what I am talking about here is electromagnetic counterparts of gravitational wave sources. So, imagine there is some source which is emitting gravitational waves, then we have these networks of gravitational wave detectors. There are 2 LIGO detectors in the US, there is Virgo in Italy, and then LIGO India is coming up soon. So, these detectors have been working hard, and they have detected gravitational waves from all these sources that you can see, the blue ones over here, and one source in between there. So, let me explain all of this. So, gravitational waves, broadly speaking, you will have another module which deals with it in detail, but are created by asymmetric motion of masses. The first direct detection happened in September 2015, and what generated that is a merger of 2 black holes, and that is what you see over here in these diagrams, which is that say this black hole and this black hole merged to give this black hole. Okay. The black holes which are shown in purple are all black holes that had been detected from X-ray binaries until then. Okay, and what you see at the bottom over here and a lot of them over here are neutron stars whose masses are known, and again these are neutron stars which were seen either by radio telescopes or X-ray telescopes. But what I want to draw your attention to is this particular system in between. This was a event which was detected on 17th of August 2017, and this was the first time LIGO actually detected the merger of two neutron stars. So, these two objects spiraled into each other, collided and emitted gravitational waves in the process which were detected. But what is different from all of these black hole events which were discovered at the top is neutron stars actually do emit light. Okay, so, next I am going to show you an animation of what actually happened there. So, we have these two neutron stars over here, and the distortions of space time being caused by them are also being rendered in this, and as they come towards each other and collide, what actually happens finally is that they emit this giant jet. There is a lot of ejecta that is coming out of them, and all of this going together, okay, is what was detected. So, what is seen at the bottom here is the gravitational wave signal which was detected by the gravitational wave observatories. But what is equally interesting is this spike over here. You will notice that this looks like the GRB detections I talked about, and that is exactly what it is. The three plots that you see here, the top two plots were detected are measurements by a satellite called Fermi, and the third plot are consists of measurements by a satellite called Integral. So, just about 1.7 seconds after LIGO detected this merger, these two space telescopes actually saw a burst of gamma rays coming from roughly the same part of the sky, and that actually was the first time that we could verify that these short gamma ray bursts that we talked about a few slides ago actually arise from the merger of two neutron stars. Okay, and this event happened at a distance of about 40 megaparsecs from us. So, about 130 million light years ago. So, although I am talking about it as the 17th August 2017 event, in reality it is a 130 million year old event. There are many other satellites which are out there which detect gamma ray bursts. So, why did only these two see this and why not others? So, I can show you AstroSat as an example. So, various things are plotted here. This small green box that you see, this green oval that you see in the center here is where LIGO finally localized that the source must have existed. The brownish circle that you see which is marked as GBM is where Fermi said the source would have come from. And then you have this large circle drawn across the globe over here, this one, the blue band, and that is where Fermi plus Integral together figured out where the source must be. So, these two working in tandem essentially are like how your ears localize where a source of sound is. So, your brain computes the difference between time of arrival or a frequency offset or a phase offset rather between your two ears, and that can tell you that okay, the source was somewhere in that part. So, similarly, the slight time delay between when Fermi saw the burst and when Integral saw the burst actually allowed astronomers to say that it must have lay somewhere in this blue band over here. But you can also see that the globe is divided into a dark grey shaded region and a light region. The light region is the part of the sky which was hidden behind Earth as seen from AstroSat at that point. Okay, so, AstroSat was sensitive enough to detect this source, but the source was behind Earth. It would have become visible in about 300 seconds, but we did not see it, and that actually was great news because it allowed us to say that it must lie in this part of the sky. We are so sure about the performance of our detector that the very fact that we did not see a source this bright means that it must have been in this part of the sky. And I am going to go a little bit into detail here into this story. So, we saw a gravitational wave event, and we also roughly at the same time saw something that was detected by Fermi and Integral. So, we saw a high energy trigger, and that was not just that, people also later found an optical source in that part of the sky which was later discovered in UV, in infrared, in radio and everything. So, these three events are actually three independently or not completely independently, but three events detected in different wave bands by different satellites, different telescopes. How do we actually know that these three are related and they are actually the same event? So, that took a lot of effort, okay, and that effort which was put in. So, how do you know that the gravitational wave source for example is the same as the gamma ray burst that was seen? And we talked about this purple localization region and the blue band and so on again. So, what are the odds? We see roughly 1 gamma ray burst per day. So, what are the odds that we will see a gamma ray burst randomly in the same direction as where LIGO saw this event, and that if you calculate the probability is about 0.1%. The next question that you can ask is what are the odds that a source, a gamma ray burst will explode at the same time anywhere in the sky as when LIGO saw this. Now, the question of course is what is the same time? It is clearly there was a 1.7 second offset. So, this was something that astronomers had thought of beforehand, and they had decided that a 100-second window roughly is enough. If we detect a gamma ray burst which is more than 100 seconds offset from a gravitational wave event, then we can't think of a physical reason why those two would be associated, and we would call them as independent events. So, again that gives you order of a 0.1% chance that they would happen at the same time, and that put together what it tells us is that there is only a 10 raised to minus 6 false association probability, 1 in a million chance that these two are unrelated. That is pretty good, that is confident association. And similar work then was done. So, here what I have shown is some optical spectra. I know we are talking about high energy here, but for completeness I am mentioning this here, which is that we looked at this source and it did not behave like any other known classes of sources, but the spectral and temporal evolution, how the brightness and the spectra were changing with time, was consistent with theoretical expectations for what a gravitational wave counterpart afterglow should look like. Remember, this is the first time that such an event was seen, and it is this detailed effort. This involved about 3,500 astronomers from 950 institutes working together in order to actually understand what happened here, and all of these being exactly the same. Sorry, it was 3,500 astronomers. Okay, so that brings us to our next component, which is how do you study high energy transients. Okay, so we have talked of some variables, we have talked of some transients. How do you actually go about observing them? And okay, why does it have to be something special? Well, what are the properties of a transient that we want to know? As before, we will start with there is sky coordinates, where on the sky was did the transient happen, but we also want to know how far away it was. So, there is distance. Other than that, we want to know when the explosion happened, what is the time of the explosion, and how did it evolve? Did it last for 1 second? Did it last for 100 seconds? Did it brighten up very quickly and slowly fade off, or did it brighten slowly and fade off slowly quickly? What exactly went on there? And other than that, we also want to know what the spectra are, because the spectrum is going to tell us about the emission mechanisms in the source, and to understand those emission mechanisms, spectra in high energy might not be enough. We actually might have to go for multi wavelength follow up of these sources. So, what exactly did we see in say optical wavelengths, what did we see in radio and so on. But for all of these properties there are some problems, and the problems are that we do not know when the transient is going to happen, we do not know where on the sky it is going to happen. Not only that, even if a transient does happen, that position might not be observable by you at that time, as happened with AstroSat for GW 170817. The transient itself might be short lived. So, 300 seconds later, when AstroSat got into a position where it could have seen it, the transient itself lasted for a fraction of a second. So, we could not see it. Or if you are looking at variables, the problem is that the variable might be faint or the variability might be small. So, the brightness might be changing by just 1 or 2%. So, you need to have an instrument that is sensitive enough to be able to see this. So, with all of these observational constraints, what does it translate to in terms of mission requirements for whatever instrument that it is you have, that you want to search for transients, you want to detect transients. So, first is it has to have a large field of view. You want to be observing as much of the sky as you possibly can with good angular resolution, right. So, if I just have a camera which is open and it will tell me, oh, something exploded, but I have no idea where it exploded on the sky, that is not good enough either. And then next we want to have continuous coverage. I do not want to have an occasion where, oh, I was observing for 23.5 hours, but in the half an hour that I went for a tea break, transient exploded, sorry, I can't help it. You also want to have a wide energy band, because you want to study the spectrum of this object, and especially in the case of short lived transients, you want instant communication. So, you can't, if you have a satellite which is orbiting Earth, you can't have a scenario where you wait until the satellite passes over your hometown again so that you download that data, because that a low Earth orbit is typically a 100-minute long orbit, and in 100 minutes the transient may have faded away drastically. For example, supergiant fast X-ray transients that we have talked about, they can fade by a factor, brighten or fade by a factor of 10 in a matter of minutes. So, if you go there 100 minutes later, the source might already be too faint to be seen. Okay, so, now in order to study these properties of these transients, we are actually going to use astrosat as a case. So, to study properties of these transients, let us look at astrosat. This is a fully Indian space mission. So, here is what astrosat looks like. We have 5 independent telescopes on astrosat. So, this pair here is the ultraviolet imaging telescope sitting right at the center. Then next to it we have the soft X-ray telescope. Then we have 3 modules of the large area X-ray proportional counter. This instrument here is the cadmium zinc telluride imager, and then off to a side we have the scanning sky monitor, which you can see is over here. Okay, so, 3 of these instruments actually are what I am going to talk about in the sense of studying say transients and variables. Okay, so, the first one that we can think of is these boxes over here, which are the large area X-ray proportional counter. What these do is that they look at one direction in the sky and they can see only about 1 degree of the sky at a time. So, that is roughly factor of 4 larger than the full moon, roughly speaking, factor of 2 on each side. So, area wise a factor of 4, and in that LAXPC actually has the most sensitivity of any X-ray instrument ever built for that kind of an observation. So, LAXPC with its huge collecting area collects a lot of photons, and it has measurement accuracy of 20 microseconds. So, it can measure the arrival time of these photons extremely well and look for variability on time scales. This is fantastic for studying black hole QPOs, for example. We looked at an example of that already, and variability studies which are at to be done at fraction of a second to tenths of second time scales or even minute time scales, LAXPC is fantastic. But the problem is LAXPC can see only one small part of the sky. What if there is a transient which explodes somewhere else, or what if there is a X-ray binary in some other part of the sky whose brightness changed during this time while you are concentrating on one source. So, to solve that problem, we have this unit on the side which is called a scanning sky monitor. So, behind me here you can see one of the 3 modules of the scanning sky monitor, SSM. SSM consists of these 3 units which are wide on one side and are narrow on another, and they each unit sees about 100 square degrees of the sky. So, this is roughly 100 times larger than the field of view of LAXPC. The sky is about 41,000 square degrees, and so what the idea is that we observe a wide field, a wide part of the sky. Each of the 3 units looks at a slightly different part of the sky. You stare at it for about 10 minutes, so that you measure the brightness of every source. During that 10-minute stare, you measure the brightness of every source in that region, and then the LAXPC units actually rotate slightly, so that you now see a different part of the sky. So, while astrosat, suppose in this orientation, is observing a source at the top, LAXPC is studying this part of the sky completely. So, this is fantastic for studying variability on say timescales of minutes or longer variability. So, now what you are doing is you have measurement of the brightness of every source in the sky over a period of days. You are seeing it every single day and you are measuring its brightness. So, variabilities which are longer than days, a scanning sky monitor is the kind of idea that you want to use. But what if your transient actually lived only for a second? So, SSM was pointing in this part of the sky, something exploded here, 10 minutes later SSM looked there, but the source had already gone. So, for that you need an instrument which is continuously seeing the entire sky, and in this case this instrument for us is the cadmium zinc telluride imager, which is this box here or this box behind me on screen here. So, CZTI actually is designed to be have a primary field of view of about 6 by 6 degrees. So, about 36 square degrees roughly, depending on how you count. And CZTI, the interesting thing though is that energies above 100 keV or so, it actually is open to the entire sky. So, all of this metallic structure that you see here becomes transparent to, or not becomes, is transparent to photons of energies above roughly 100 keV. Okay, and what it means is that what we see over here is what is called the effective area, or you could think of sensitivity. Okay, and this is sensitivity of CZTI for the entire sky. So, the bright yellow regions that you see near the center are where we have maximum sensitivity, and you can see that there are relatively few areas in this plot which are black, okay, which are dark. So, what is happening is that this is astrosat. If a transient explodes here, CZTI actually is transparent to it. If a transient explodes here, we get all the photons, we can detect it. On the other hand, if a transient exploded here, then all those photons actually have to travel through the satellite before they can reach CZTI, which means that most of them are going to get absorbed or scattered by the satellite, so we won't detect that transient. But this is the kind of all sky monitors that you need if you are looking for gamma ray bursts or other transient events, counterparts to say gravitational wave sources, which last for a very short duration of time. Okay, these are transient sources, but they are extremely bright. So, despite you not having the full sensitivity that any of these pointed instruments have, you will be able to see them with a continuous all sky monitor. So, these are the three ideas. We have, if you want to take one source and you want to study its variability in great detail, then you have an instrument like LAX-PC. If you want to just measure the brightness and variability of X-ray binaries over extended periods, you use an instrument like the scanning sky monitor. And if you want to study gamma ray bursts and other events which are extremely short lived, then you use all sky monitor like CZTI. Now we have data that is coming in from these sources, and it should look like it is straightforward to actually detect transients in that, but that is why we are going to spend just a little bit of time in realizing the complexities in that. So, here is raw data from one orbit or a few orbits, actually one observation made by the cadmium zinc telluride imager, and here is what the raw data looks like. You see all of these spikes over here. All of these spikes are noise, okay, they are not real astrophysical sources, and you can see especially over here this and this here, this forest of lines. This detector was just misbehaving during this part of the orbit. Space is an extremely hostile environment. You try your best to create things which are space proof, which will not break up, which will continue to function reliably in space. But despite that, raw data actually needs to be pre-processed quite drastically to get rid of all of these problems, so that you then have data which is free from onboard noise, which is free from charge particle event counts and so on. So, you want to be able to separate what is a real astrophysical transient, something which happened in the sky, as opposed to something which happened locally in your instrument. So, even after cleaning, what you see now, this data behind me over here is from a different orbit now, or different set of orbits, and is cleaned data, but you can see that there is still a lot of features here. You can see data actually count rate dropping all the way to 0 in between, and that is when either the source goes behind Earth, or there is this region over the South Atlantic Ocean which has a high density of charged particles, and the noise there is so much that you simply have to switch off your instrument. This is called the South Atlantic anomaly, or SAA. So, there are all of these other problems that you have to take care of. You try to clean the data and you then try to process it, and then you start looking for transients. So, just to again give you a qualitative feel of how this is done, here is a spectrogram or a time energy plot of CZTI for a small interval. So, the time on the x axis is plotted in seconds. So, this spans just about 1000 seconds of data. On the y axis here we have energy going from 20 keV all the way to about 200 keV. On the x axis time is progressing from here towards that direction. You can think of this roughly as the equalizer that you would see in say music playing software on your computer. Okay, so, what I am doing is that at each instant of time I am measuring the spectrum of whatever I am seeing in the sky, and then roughly at around this point you see that there is probably a spike. Okay, I see enhanced emission at all energies, but then I also see something like that over here. So, which of these is actually a real spike, which of these is not? Okay, so, we then have to process data further, we further suppress background. After suppressing background, you can see that this first enhancement that we saw still seems to hold good, but what we had seen over here is not probably that prominent. We can do better, we can actually apply more statistical techniques to find out the significance of all of this, and finally you can see that there are two lines here, this and then this one, and that is actually a real gamma ray burst. We know also there are several other cross checks we use. In this particular case, we know that this was a burst seen by others. This was a GRB detected in 2016 on the 2nd of December, hence the name GRB 161202A, the first GRB detected on the 2nd of December 2016. Okay, and you can see clearly over here that there are two spikes. Okay, there is one over here where you see a lot of photons, and then after about some 70 seconds or so there is another spike which is giving you a lot of photons, Astrosat, we can see that after all of this data processing and cleaning, we have seen both the spikes. What is marked here by the dashed red line is when another satellite saw this, and you can see that clearly that satellite missed the first spike, but it saw only the second one. What if another satellite had not seen this? That is where again the 4 quadrants or 4 identical instruments come into place, where here what we are seeing is light curves in 4 colors again for these 4 independent instruments. If you have electronic noise or other detector problems, pixels misbehaving, then that noise cannot be correlated across all 4 detectors. If you have charged particle events which are looking like photons, it cannot be correlated across 4 independent detectors. So, it is important for us that we actually see it in more than one quadrant, and if you look carefully over here, you can see that in some quadrants the peak is quite high, in other quadrants over here and here the peak is rather low. That actually allows us to figure out roughly what part of the sky the transient actually happened in. So, this is just to give you a glimpse of the behind the scenes activity. It is important to have a feel of the complexities involved in data analysis. Right at the start we said that X-ray and gamma ray detectors actually measure multiple photon properties, and in that sense are better than optical detectors, because you are simultaneously getting time of arrival of individual photons, you are getting energy, you are getting position, but all of those extra benefits come with their extra problems which actually have to be solved and looked at carefully before you can analyze the data. We are coming close to the end. Let us look at some other leading time domain missions. So, the most popular mission for detecting GRBs arguably is this one, the Neil Gehrels Swift Observatory. It is a satellite that has revolutionized our study of gamma ray bursts, and then here we have the Fermi Gamma Ray Space Telescope. On this side, on this side here we have NICER, the Neutron Star Interior Composition Explorer, which is a very recent experiment that has flown on board the International Space Station, and that is really giving us a lot of new insights into the behavior and physical properties of neutron stars and actually even some black hole sources. Now, all of these missions when we are looking for gamma ray bursts or other very short lived transients, it is also very important that we have to have a global follow up network in order to successfully study these. So, this is a slightly old plot over here. So, you see some of the older missions that were dedicated to studying transients. All of the data downlinked from them is immediately circulated over this network called the Gamma Ray Coordinates Network, or GCNs for short, and this GCN network actually works in 2 modes. So, you can actually have an automated notice that goes from a computer to another computer, and then you can have optical telescopes on the ground which are coordinated and can directly start observing. So, we have just installed a new fully robotic telescope in Ladakh in India, for example, which will respond to these kind of notices. As soon as there is a gamma ray burst, whether it is at 8 p.m. or 4 a.m., whether the astronomer who is supposed to be there does not need to look for that transient and then start observing it. The telescope, as soon as it gets the machine readable notice, will process it, decide based on some conditions that we have set beforehand, and start observing the source right away, so that you can catch the source before it becomes too faint to be detected. But then after we have obtained that data, after we have analyzed it, we also have these human readable notices which are published, which is where we then send out our results saying, yes, our telescope immediately slewed into action, or we got up and we told our telescope to point there and we studied that source, and here is what we have found from our studies, here is what we have learnt about the source. So, this prompt coordination is extremely important. There are networks, not just another problem of course is, what if suppose it is say noon in India and there is a source which is visible only in India right now, it is below the horizon for say telescopes located in Europe or in Americas, and you now want to observe it. Well, then you have to use a space based telescope to do that. Or what if I have a very good telescope here, but it is daytime, then I have to have a network where I have some other telescope in night time where that can be observed. So, one such network that we have is this one called the Growth. This is just one of many international collaborations. And it is, you can think of it as a relay race. Okay. So, I have Earth over here, the sun is at the bottom. Imagine Earth as it is spinning around, and suppose there is a transient say up here. Okay. So, different telescopes in this network will be able to see this transient one at a time, and it is guaranteed by having this large set of telescopes longitudinally separated from each other, that at least some telescope will always have night at their location. So, at least some telescope will be able to observe it. This is to emphasize again the global nature of science today. No single instrument, no single telescope or observatory can any longer study these sources, and collaboration rather than competition is extremely important. Working with collaborators around the world, everyone contributes their expertise, whatever they are good at, and then the sum of all of this is way more than the sum of individual parts. And not only about ground based networks, there are now plans to actually have networks in space. We talked about how IP and integral and Fermi together could create that narrow blue band on the sky where the source would have been located. Now, instead of that, if we have multiple satellites, suppose we have say 10 satellites or why not even 100 satellites all around Earth, which are constantly monitoring the sky, and then when these satellites actually detect an explosion, you could use them very similar to the way that a GPS system works. You could actually use these satellites and you can figure out exactly where the explosion happened. That gives you great amount of redundancy. Each satellite can have its own specialities, it can have its own different energy bands of observing, different fields of view, different resolutions, and all of these satellites working together actually can give us a lot more information. So, there are multiple proposals like this. There are proposals in India, proposals abroad for detecting gamma ray bursts. There are even student projects around the world to make satellites which are about this small, okay, CubeSats, which can actually detect gamma ray bursts. So, there is a lot of development happening here. There are also more and more advanced narrow field telescopes which are being developed, and these telescopes would actually then receive triggers from satellites like these, and based on those triggers we could point them there and start more detailed studies. So, we will conclude with that, and in summary, the high energy sky is highly dynamic. Everything, every source is variable at some extent on some time scale. The spectra and intensities of all of these sources, X-ray binaries, active galactic nuclei, they all keep changing with time. We see variabilities going from time scales of microseconds to time scales of years in case of active galactic nuclei. And then we have these massive explosive events like gamma ray bursts, novae, supernovae and so on, which are extremely bright in high energy bands, and they are often primarily detected in high energy bands. And finally, the global community very quickly initiates multi-wavelength follow up of such kind of sources, and the goal behind any kind of follow up like this is to understand the physics, the underlying physics of all of those sources. With that, we close our session on time domain high energy astrophysics. Thank you for your attention.